Now let us look at delete operation from heap. Already a max heap is given here and I want to delete. So which element I should delete? Shall I delete 25? Shall I delete 35? No. The very important thing. From heap you can delete only root element. Which element is there in the root? Largest element. This is max heap. So largest element. So when you want to delete, you can delete only largest element. You cannot delete any other element. So a hint here, it means you can delete highest priority element. Yes, you can only delete highest priority element. Yes. Now, how to delete that 40? Okay, I will take out 40 from here. 40 is gone. Let us take it in some temporary variable, hold it for some time. Then which element should come here? Common sense says that 35 is greater, so it should come here. Okay, I will send 35 there. Then who should come here? 15 is greater, so 15 should go there. Okay, 15 will go there. Then see the problem. Is it a heap? It is not a complete binary tree. It's not a complete binary tree. So if you try to adjust the element like this, it will not be a complete binary tree. Then what is the solution? Look at this once again. I'll put back the elements, 15 as it is, 35 as it is. This place is vacant, 40 is gone. Copy the last element in complete binary tree order at this place. So bring 5 at this place. Bring 5 here. Yes, that's perfect. So 5 is removed from here. So when the root goes out, the last element in complete binary tree should take its place. So I'll remove this from the diagram. This is gone. Now this is a complete binary tree but not a max heap. So I have to adjust the element, rearrange the element so that it becomes a max heap. Before showing you how to adjust the element, let us do the same thing in an array. I will take out this value 40, that is root, the very first value. It is at index 1 in variable x. And I will bring this 5 at this place, so 5 is copied here. Now heap is till index 6, 7th location is empty. Now how to adjust these elements to form a max heap? For this, the procedure is compare children of new root. Children, compare who is greater. This one is greater, this one is greater. Then compare this one with the new root. So root is smaller than this one. So interchange. 5 comes here, 35 goes there. Then continue. From here, compare its children. Which child is greater? This is greater. So interchange 5 with this one. 5 comes here, 15 goes there. Now from this place, there is no left child or right child for this node. So stop. So the procedure was compare the children. First find out which child is greater. Then compare with the element. If the element is smaller than any of the child, then interchange with that child. So now it is perfectly adjusted. It is forming a heap, max heap once again. So here if I show it in an array, then this is the element that I have to adjust. Compare its children. So who are children? If this is I, then 2i, 2i plus 1. Compare these two. If I is at 1, compare its left child and right child. This is greater. Then compare this child with the parent. So parent is smaller than the child. So interchange them. So this becomes 35 and this becomes 5. This is one step that we have seen it here, right? 5 came here that time. Now again its children. This is 2. So 4 and 5. Compare these two children. Now let us say I is here. I is at this place. So compare its left child and right child. Right. So let us take J. Which is greater? This is greater. So let J be at that same place. So interchange the value at I and J. So 15 comes here and 5 is copied here. So these are interchange. Then take I to the place of J. This is the new location of the element that we are adjusting. We have adjusted 5, right? Now, where is the left child of this one? So that is 8. 2 4 8. So 8 is outside the heap locations. So that's all. Stop. So this is how deletion works. I will write on the procedure. So here is a delete function which is taking an array, this array, and n is the size, that is last index 7. So this last index element, I will take it in variable x. A of n is taken in x. This element is deleted. Then copy the last element at this place. A of nth element is copied at first place, that is index 1. Then we need I on the element that we are adjusting and j on its left child. So I is at index 1, j is at its left child. Now the procedure is repeating. So I have to write a loop. So I will write while loop. What I have to do every time? Compare left child and right child. Whichever child is greater, let j point on that child. See, wherever j, suppose j is pointing here at 4, then right child is next element only. So a of j plus 1, if it is greater than j, then move j to right child. Like j was here, so I was here, and element 5 was here and 15 here. Compare a of I with a of j. If a of I is smaller, then interchange a of I and a of j. If the parent element is smaller than child element, then interchange parent and child, and also bring I at that place of j. So I will come at the place of j, elements are swapped, then j should go to its left child. So j should move on to 2 into j. If the parent element is not less than child element, if it is greater or equal, so we don't have to swap and we don't have to go further. Stop. So I will say break. That's all. These are the steps. Compare left child and compare right child. If it is greater than left child, then move j, and compare with the element a of I with a of j. If element is smaller, then swap with a of j. Then take I on j and also move j to the left child. So this loop should continue how long? Until you reach the end of this heap. So what is the end of the heap? The last index was 7, so it should be 6. So if last index was n, then it should be n minus 1. So while j is less than n minus 1, we have to continue. That's all with the delete. Now I have not closed delete. I have to show you something more. So this procedure you have to trace it by yourself once, then you can remember and again you can write on by yourself. Right? So take some bigger size heap. You take some 15-20 elements and then you try it. You can clearly see the things working. So that's all, we have completed delete. I will repeat the points once again. So always root element can be deleted and the last element in the complete binary will take its place, and then we adjust the element by sending it downwards towards its children. So whichever child is, if a child is greater, then that child will interchange with the parent, and we try to adjust the element. So we have adjusted 5 just now. So similarly, if I delete once again, I can delete only 35, then who will take its place? 25. 25 will go there and 25 will be adjusted. That's it. So this is how we can delete as many elements as you want. Now listen, very important thing. See, we deleted 40. 40 was gone. And this is a new heap with 6 elements. Earlier 7 elements were there. Now the heap size is 6 only. But in an array, one space is vacant. Is it a part of heap? No, that is outside heap. So the element that I have deleted, shall I keep it there? Yes, I can keep it. Is it a part of heap? No, this is outside element. It's not in a heap. 40 is stored at a free space after deletion, right? Now delete again. Which element you get? 35. What will be the size of a heap? 5. This place will be free. Shall I store 35 there? Yes. Then next, which one will be deleted? 30. Next, 25. Then 15. Then 10. Then 5. What happens to the array? Sorted. Yes. Yes. This is heap sort. This is heap sort. So what is heap sort? From the heap you to go on deleting the elements, and as you go on deleting the elements one by one, you get a free space at the end of an array. Use that free space for storing the deleted element. So the elements will be getting arranged from last element onwards. That is, they will be arranged in descending order from the right hand side onwards. So finally they will be in ascending order from left hand side onwards. That's it. This is the heap sort. Let me show you one thing. See, in this delete, I said I did not close the bracket. What I will do is, deleted element was in X. I will copy it at this last free space. So last free space is N. So at A of N, I will copy X and then close. So what this delete function is doing, deleting an element and copying it at last place. Now I will show you heap sort. Heap sort, first step, create heap of n elements. Create heap of n elements. First create heap. Already in the previous video we have seen how to create a heap by inserting elements one by one. Elements are in the array only. Same array, the elements will be inserted. How to create a heap we saw. Create a heap. Then after that, go on deleting the elements from the heap one by one. And start copying the elements at the free spaces which we are obtaining after deletion. Copy the element at free space. So delete and copy, that's all. Delete n elements one by one. That's it. So create a heap of n elements, then delete the elements one by one. That's all. It became a heap sort. Create heap of n elements, delete all the elements. The deleted elements, start arranging them. It's a heap sort. So for understanding heap sort, we must know how to create a heap and how to delete the elements from the heap. Then heap sort is nothing. See, it is just like we have some set of elements. So we are inserting in the heap, dipping in the heap and taking out the elements from the heap. They are sorted. So that's all about heap sort. Now let us do some analysis. How much time that create heap was taking? Create heap was taking n log n time. Yes. Then how much time one delete is taking? One delete means the element is adjusted. So how much time it is taking depends on the height. So for one element, deletion of one element, log n. For deletion of all n elements, n log n. So deleting all elements also n log n. So total time taken by heap sort is 2n log n. So this is order of n log n. So it is order of n log n. I will write on the complete program for insert also, delete and create heap and deleting heap. Then also finally I will show you heap sort. So that's all finished.